Welcome to The Explainer. I am absolutely thrilled to have you here today because we're diving into a topic that honestly feels a bit like science fiction but is an everyday reality for modern mariners. We're going to explore the hidden vulnerabilities of modern maritime navigation. We live in this era of digital perfection, or, well, at least we think we do, where glowing screens tell us exactly where we are down to the actual meter. But today, we are pulling back the curtain on those bridge displays to uncover what we call the trust but verify arc. Let's get right into it. So, let's start with a rather chilling what-if scenario. What happens when your ship's most trusted navigation system suddenly lies to you? I'm not talking about a power blackout or a blank screen. I mean a flat-out lie. Imagine you're navigating a massive vessel through a super tight channel. Your screens show you perfectly centered, safe and sound. But reality outside the window is something completely different. It kind of shatters that illusion of absolute technological reliability, doesn't it? And really, that exact nightmare scenario is why official guidance exists. As MGN 379 states, be aware of the dangers of over-reliance on the output from and accuracy of a single navigational aid. This isn't just some academic theory or a gentle suggestion. This is crucial life or death guidance directly from maritime regulations. Relying on just one single screen is quite literally a recipe for disaster. To understand exactly why that regulation is so critical, let's kick things off with Section 1, the limits of GNSS. Now, we all place an immense amount of comfort and reliance on satellite navigation. It's essentially the heartbeat of a modern bridge. This brilliant global web of global navigation satellite systems, things like GPS, GLONASS, and Galileo, gives us 24/7 positioning anywhere on the planet. It is an absolute marvel of human engineering. But as brilliant as this web of satellites hovering thousands of miles above us is, it's also fundamentally fragile. So what actually makes it so fragile? Well, you'd be amazed at how easily the universe can just throw off your position. Even minor drifts in a satellite's atomic clock or tiny little variations in its orbit can cause significant errors down at sea level. And then there's the environment. A solar storm can cause ionospheric delays that throw your position off by up to 5 meters. No way, right? Or consider multipath effects, where a signal simply bounces off a nearby building or a harbor crane before it actually hits your receiver. In a tight waterway, just a few meters of inaccuracy can literally mean the difference between a safe passage and a catastrophic grounding. But, nature isn't our only adversary here. That brings us to Section 2, the GPS jamming threat. Let's shift the tone for a second and face a pretty stark reality check. What happens when the signal isn't just delayed by a solar storm, but is deliberately attacked? Back in the 2008 GPS jamming trials, during deliberate service denial testing, a ship's recorded GPS position was shown to be completely on land. It was a massive 22-kilometer error compared to where the ship actually was out in the water. 22 kilometers! If your bridge systems are blindly trusting that GPS feed, your ship essentially thinks it's cruising straight through a coastal town. And the cascading failures during a jamming event like that are honestly terrifying. Shoreside, the vessel traffic services picture gets incredibly confused, but on the ship itself, it's so much worse. If you have an integrated bridge system running a passage plan on autopilot, that sudden jamming can cause the vessel to alter course violently without ever warning the watchkeeper. Add to that the sheer volume of alarms sounding all at once, distracting the crew at the exact moment they need maximum situational awareness. So, what's the solution when GNSS fails? Let's dive into Section 3, radar and ELORN backups. When the sky falls silent or starts lying to us, we have to rely on terrestrial, Earth-based backups. But before we even look at position, we have to know our movement. The crucial distinction here is between your speed logs. A Doppler log tells you your speed over ground, while an electromagnetic log tells you your speed through water. When your satellite data drops out, knowing your actual physical movement through the water versus over the ground, especially when you're dealing with strong tides, becomes absolutely critical for dead reckoning. Okay, back to position fixing. Remember that 2008 jamming trial where the GPS was 22 kilometers off? Well, an Earth-based system called eLORAN proved completely unaffected by it. With really robust coverage in the northern hemisphere, eLORAN relies on terrestrial radio transmitters rather than space-based satellites. Because of that, it acts as an incredibly robust, independent backup to GNSS, giving you accuracy that's very comparable to standard GPS. But listen, your most immediate failsafe, the one right there on the bridge with you, is radar. Now, it definitely has limitations. You need to be within 20 miles of land or a conspicuous target, and you absolutely must be aware of shadow sectors and blind spots. But a properly calibrated radar gives you range accuracy within 30 meters and bearing accuracy within 1 degree. It is literally the ultimate tool for cross-checking your satellite position against your actual physical surroundings. Now, let's pivot from how we find our own position to how we see everyone else out there. Section 4. Decoding AIS data. The Automatic Identification System, or AIS, is the communication web connecting vessels across the sea. So what exactly is AIS broadcasting? The data breaks down into 4 main categories. You've got static data, which are fixed things like the ship's name and its MMSI identity number. Then there's dynamic data, which is the automatically updated real-time stuff, like your position and speed. But pay really close attention to the voyage-related data. This includes the destination, the ETA, and the draft. Why? Because that data is entered manually by a human being. And that right there brings us to the great illusion of AIS perfection. It's an incredibly useful tool for sure, but it is deeply vulnerable. Because voyage data is manually entered, it is totally subject to human error. We're talking wrong destinations, incorrect drafts, plus AIS can be spoofed, signals can overlap in congested waters, causing annoying delays, and here's the kicker, military ships, small craft, and fishing vessels might not even be transmitting at all. If they aren't on AIS and you aren't looking at your radar or looking out the window, they are practically invisible to you. But AIS isn't just for tracking other ships anymore. It's actually changing the physical seascape itself. Let's look at Section 5, Virtual Aids to Navigation. So, electronic signals are slowly replacing physical steel and concrete, which means you need to know exactly what is and isn't physically in the water. A real AIS aid to navigation, or ATON, means the transmitter is physically sitting right there on the actual buoy. A synthetic ATON means the buoy is really there in the water, but its AIS signal is being broadcast from a remote station on the shore. But a virtual ATON? That means there is absolutely no physical object in the water. Nothing. It exists entirely in the digital realm, usually to mark a sudden temporary hazard, like a brand new shipwreck. So how in the world do you tell the difference on your screens? It comes down to the diamond symbology used on your ECDIS navigation displays. Solid diamonds indicate that a physical object is actually out there, but dashed lines forming a diamond? That dashed symbol tells the watchkeeper instantly that this is a virtual ATON. It is a digital-only marker. And the symbology gets wonderfully specific to help you instantly recognize what kind of hazard you're dealing with. For example, emergency wreck marks are noted by a cross on top, and cardinal beacons are indicated by triangles pointing up or down. Whether they are physical or virtual, recognizing these shapes at a single glance is absolutely vital for navigating safely around sudden dangers. But what happens when the digital marker breaks? Well, the system is designed to warn you. If an ATN has a failure or drifts off its designated position, your screen is going to flag it using a bright yellow caution color and text labels like unlit, missing, or off pause. A watchkeeper has to be highly trained to spot and interpret these yellow anomalies the second they appear. Which perfectly sets up our final topic, Section 6, the watchkeeper's responsibility. Because at the end of the day, all of this amazing technology, the satellites, the radar, the AIS, the digital buoys, it all funnels down to one single place. It funnels down to the human on the bridge. You are the ultimate failsafe. These core best practices are non-negotiable. You absolutely must verify AIS data with radar. You must use electronic systems as supplementary tools for situational awareness, not as your sole method for collision avoidance. A watchkeeper has to continuously synthesize data from every screen, every log, and every window. You can never, ever rely on just one source of truth. Let's revisit the core philosophy of our explainer today and look at this final regulatory rule from the MCA guidance. They are supplementary aids and must not replace visual or radar-based navigation. That is the absolute ultimate takeaway here. Technology is an aid. It is a tool. It is not the navigator. You are.
So, I want to leave you with this provocative final thought to carry with you on your very next watch. If your screen suddenly blacked out, or worse, if they actively lied to you, are you ready to look out the window and navigate? It's all a question of eternal vigilance. Study your backups, trust your training, and always cross check your data. Thanks so much for joining.